in a somewhat different context. This is an outline of my talk. So I'm going to show you some photonic simulators of topological solids. First, I'll deal with the integer quantum Hall effect and how this can be implemented with magnetoelectric photonic crystals or chiral metamaterials. So actually it's the first and second arrow here. And then how we can implement the integer and possibly the fractional quantum Hall effect with microwave photons and microwave Haldane lattices. Then I will move to simulators for topological insulators and some system, 1D coupled cavity system which can simulate zero-dimensional topological states, which somehow an analog of Majorana states, and finally some plasmonic materials which we can simulate the Dirac equation. So I will first let me give you an introduction for those of you who are not familiar with this. If we have a typical insulator, then we all know that we have a band gap in the electron band structure, and this is also a typical insulator, the quantum Hall effect, quantum Hall state. In the presence of magnetic field, the electronic states have they are like the well-known Landau levels. So the real difference between these two types of insulators, it's their topology. The one has a topology of spherical or almost spherical shape, the other of a torus. I suppose most of you know that all these are quantified with typical quantities like the chair number, which characterizes the nature of the topological nature of the bands. Other relevant quantities are the Baire flux, the Baire curvature. They are calculated based on the wave function, the block wave function of the electrons of the solid. So in the conductance is dependent on this chair number. So actually, when the system is topological, then it's given as an integer multiple of the quantum of conductance. So an analog of photonic, the first photonic analog of the quantum Hall effect was first introduced by Haldane and Argaud back in 2008. So it was actually a two-dimensional photonic lattice made of magnetoelectric rods. And this is actually a honeycomb lattice, the 2D lattice of graphene. By suitably choosing the parameters of the system, we can have a Dirac point in the frequency band structure of this photonic crystal. So this is a 2D map of band structure too. So what happens, for example, in graphene for the electronic states, if we choose a magnetic field, but which is also periodic and contains the periodicity of the lattice, then we can actually introduce the quantum Hall effect in graphene. So Argaud and Haldane thought the very same thing for photons. So they actually propose that if one somehow breaks times reversal symmetry in such a system, then this the Dirac point may turn out to be a Dirac gap, and all these nice things of topological stuff that occur in graphene may occur for photons in such a crystal. So the idea is here that in order to break time reversal symmetry is that we use not a plain dielectric material but a magnetoelectric material, which is provided, which also contains a magnetic permeability tensor, which looks like that. It has these off-diagonal terms which explicitly break time reversal symmetry. So the first experimental demonstration was in the microwave regime, where magnetic materials actually shows such a value, such a tensor form for the magnetic permeability. Actually, this was this lattice of ferrite rods. So what actually measured, it was they have this opening of the gap in the photonic states, and for finite slabs of this crystal we may have chiral edge modes at the two sides of the 2D photonic crystal. And as you can see here from these experimental measurements, we have differences in the transmittance, in the transmission for an input wave coming in this direction, and for a wave coming in the opposite direction. This is shown here, and these are chiral topological states at the two edges of this material, and actually simulations have shown that they are pretty robust to disorder as they're supposed to be. So in all these cases we have different types of defects inserted at the edge of this material, and as you can see, the mode, the wave easily circumvents the obstacle and continues its propagation. So all these are very technologically relevant stuff, but the thing is that this should be possibly scaled down to the infrared or the optical regime. Another system which shows a similar effect are this time a plain square lattice of magnetoelectric rods. As you can see here, we have, due to the breaking of time reversal symmetry, the modes, the left and right propagating modes are inequivalent. And then I'm going further to another analogy related to the quantum Hall effect, which is the anomalous quantum Hall effect. It's about a photonic analog of a spin polarized electron gas with Rashba type spin orbit coupling. A typical example for electrons is this. It's a 2D spin polarized electron gas with spin orbit coupling. A typical Hamiltonian for such a system is the following. This is the spin orbit coupling term. This is the Zeeman term. So the analog, the photonic analog of this system, so before going into this, this is the typical energy dispersion for such a system. This is the Chern numbers for the two bands for such a system. It usually occurs in thin films, metallic films. So the analog, it's actually could be a plasmonic, chiral plasmonic material supporting longitudinal excitations such as surface plasmons. This is the Hamiltonian of the electron system. This is the constitutive relation between D, the displacement field, and the electric field for a chiral system. The corresponding dielectric tensor is written in this way. So these are the off-diagonal terms which explicitly break time reversal symmetry. So this term, the diagonal term, is the typical metallic dielectric function, which however should support longitudinal excitation. For example, a plasmonic excitation or a polaritonic excitation, an exciton, whatever, that doesn't matter. And in order to draw the analogy, the first term in the constitutive relation, it's the special dispersion due to the chiral nature of our material, and it's the analog of the spin-orbit coupling for electrons, while the other term with the off-diagonal dielectric tensor, it's the analog of the Zeeman splitting due to the magnetic field. So by solving Maxwell's equations for such a chiral system supporting plasmons, we get a non-zero Chern number and Berry curvature. This is the dispersion relation. This is for the photons. This is for the electrons. We can see the similarity between the two dispersions. The Chern number also assumes the same values as its electronic counterpart. And this is a system that could realize a chiral medium, chiral electromagnetic medium with longitudinal excitations. This is a chiral lattice of plasmonic spheres, which may be gold spheres or silver spheres. This is a typical dielectric function for such a system. So this is actually the frequency band structure for for the infinite crystal. These dotted lines are the effective medium result based on the previous slide I've shown you for a general chiral medium. This is the rigorous solution, the electrodynamic solution with a layer KKR method. This is here, this is the system without the magnetic field. If we induce the magnetic field, which induces a Faraday rotation term in the dielectric tensor, we get this picture for the Berry curvature. And the analogy goes even further with this chiral metamaterial. Actually, the analogy is quite interesting. For example, this is a typical polar semiconductor which exhibits spin-orbit coupling. This is the typical energy band structure for the electrons. This is which resembles with the a photonic counterpart for a chiral lattice of plasmonic spheres, and we have this difference here in the delta k in the wave vector, which can implement similar devices for electrons and photons. This is a typical filter for photons. This is a typical spin valve for spintronic devices. They all based on the same effect, on this dichroism of photons for the lattice of plasmonic spheres, and for the electrons for the semiconductor with spin orbit coupling. Then I'm going to further analogies with the integer n fractional quantum Hall effect. This is a system which you also observed in the previous presentation from Dr. Kyle. This is a typical Haldane lattice, a checkerboard lattice, where we have assumed first, second, and third neighbors interactions. The interactions between first neighbors have phases of opposite signs. This is the typical one electron Hamiltonian for such a Haldane lattice. We assume that we have a complex hopping among first neighbors, where this phase is not an integer multiple of pi. In the typical picture, the nice thing here is that we have one can have second and third neighbor interactions, so that one can engineer flat bands, so that to resemble the Landau levels in the fractional Hall effect, in hope of obtaining the fractional quantum Hall effect. This is the bulk electron band structure. This is the slab band structure for a finite slab of this 2D crystal to the Haldane lattice. And you see here that you indeed obtain a flat band, but most of all you obtain these chiral edge states, which are typical for topological lattices like this one. So how one can transfer this idea to a photonic system? So this is still the electron. So one can actually, in the electron system, induce interactions between the electrons in the several sites, and this way study the fractional quantum Hall effect. This is typical results. This is the ground of the first excited state for such a system. And this is a typical phase diagram for such a system. This is the region of the fractional quantum Hall effect. So in terms of photonics, we can engineer such an atomic Hamiltonian with possibly with a superconducting QED Hamiltonian. This is the typical this part is the typical James Cummings Hamiltonian. This is the kinetic part, the tight binding part, with the complex hoppings among its neighbors. So a possible realization of such photonic lattice in the microwave regime would involve, for example, the Cooper-Beer box for the case of the resonators. The tricky thing is here how one can actually put positive and complex phases in the first neighbor hoppings here. One way to do this is to use the so-called microwave metamaterials in the form of transmission lines. So this is two typical configurations of transmission lines with capacitances and inductances. So if one does solves this electric problem for an infinitely periodic transmission line, for this case we have a right-handed transmission line, which means that we have as the propagation constant increases, so does the frequency, while here we have a so-called left-handed band, where as the propagation constant or wave vector increases, then frequency decreases, which means that this way we can achieve a negative phase velocity for waves traveling between first neighbors. And this way we can have negative phases and somehow realize the Haldane lattice with these complex hoppings. Then I'm going to speak of some analogs for the topological insulators. This is actually a more interesting stuff for photonics. While if you want, for example, the main thing in photonics to have this one-way propagation, because it's very important for optical circuits. Because if you have a topological mode propagating along a certain direction, then it's robust to disorder. So this means that it's robust to lithographic imperfections when fabricating an optical circuit. So, but it is important to have some passive device without the presence of magnetic field. So the best way to do this is to simulate a photonic topological insulator, where you can actually don't need to break time reversal symmetry and still have a one-way propagation. Again, I suppose that most of you know how one can actually the remedy for making a topological insulator, as suggested by Hassan and Kane. So this is the typical picture of a topological insulator with protected topological surface states. And this is the typical iso energy contours for a weak and a strong topological insulator. As a rule of a hand, when you have an even number of Dirac-like points for the surface states, when you have a weak topological insulator, when you have an odd number of degeneracy points, you have a strong topological insulator. This is a typical band structure for a typical Hamiltonian for such a system. So it all first started with topological insulators in terms of systems with spin-orbit coupling, but then as years go by, then other types of topological solids came to surface, such as topological superconductors, topological magnetic insulators, and topological crystalline insulators, and I will focus on that. So these are systems where the respective Hamiltonian is invariant under operations of a point group symmetry. For example, for a C4 symmetry, we have these operations, and this is the typical lattice, atomic lattice, which has the property of a topological crystalline insulator. So actually this is a tetragonal lattice. So one can actually somehow engineer hopping between first, second and third neighbors, and have surface state with quadratic-like dispersion. So we can copycat this Hamiltonian for electrons with the respective Green's tensor for photons, for electromagnetic structure. So this is the photonic analog of a topological crystalline insulator. This is again tetragonal lattice, which consists of anisotropic resonators. Typically, they may have a uniaxial response. For example, this would be a liquid crystalline material. In order to engineer and transfer completely a tight binding Hamiltonian for photonics, and these things I need to embedded within a plasmonic host, so that all waves are evanescent within the host, and you have only hopping from resonator to resonator. This is the exact transfer from the electronic to the photonic power. You need to have, because in photonics it's for photons it's difficult to have actual bound states. You mostly have virtual bound states, so in order to have actual bound states of the electromagnetic field and copycat the time binding formalism, you need to have a photonic insulator, which is a plasmonic material. So this is when one writes the interaction, actually it's called the coupled dipole method or disc dipole approximation. So it actually writes down the interactions between the dipoles of the resonators, and then ends up with such a eigenvalue problem where this is the Fourier transform of the electromagnetic Green's tensor, which plays the role of the Hamiltonian for electrons. So by solving this eigenvalue problem, we get the frequency band structure of this photonic solid. This is the bulk band structure. We have the opening for frequency band gap here, and if we take the frequency band structure for a finite slab, we get this degeneracy, quadratic degeneracy here at the midpoint of the surface Brillouin zone, which signifies the existence of topologically protected surface states in this photonic solid. So and it's still Z2 topologically invariant. So one idea of implementing this in the microwave regime, a topological crystalline insulator, first of all we need to have somehow artificial plasma. Not natural plasma. Natural plasmonic materials are metals, as you know. The electric function obeys this type of behavior. For frequencies below the plasma frequency, all waves are evanescent in a metal. But the thing is that we have also losses which are very large in the optical regime. So this somehow spoils the whole remedy for transferring from the electron to the photon picture. So this is why one needs to have artificial plasma. So how one can have artificial plasma, an idea was given 20 years ago by Sir John Pendry. So one actually have a 3D network of metallic wires with a micrometer size diameter. And one can actually do with simple analytics that the effective dielectric constant for such a system resembles that of a plasmonic material, but only now the omega pi, the plasma frequency, lies in the gigahertz regime, not in the optical regime, and losses are very small because of the very small penetration length at this spectrum, at this spectral regime for the electromagnetic waves. So here is how one can have an artificial plasma, and one needs to put its resonators inside this plasma. So these resonators, which are these purple squares here, as we said, they need to have an anisotropic behavior. And these rods here are guide elements and needs to have a orientation dependent intralayer coupling between the cavities. So these are simple guiding elements which transfer the microwaves from one resonator to the other. And sorry about that. So, the coupling between the cavities, the interlayer coupling needs to be free from guiding, so it's spread all over directions. And next, I'm going to reduce one dimension in the Haldane lattice I've shown you before, and possibly see the emergence of zero-dimensional topological states. So, if one has such a binary one-dimensional lattice of resonators which are coupled with the complex hoppings with alternatively positive and negative phases, the analog with a electron Hamiltonian is this eigenvalue obeyed by the Fourier transform of the electromagnetic Green tensor. One can actually calculate the eigenvalues and the frequency dispersion for such a lattice, which is the same equation for the as the Bogolyubov-Descent dispersion of Kitaev's model. One can actually prove that they are indeed topological bands by calculating Zach's phase for one dimension. And it turns out that within the gap of this lattice, for finite sizes of this lattice, one can have zero modes. It's localized zero-dimensional modes. Which are localized at the edges of the gap, and they are by putting some disorder in our system. So here we put some arbitrariness, some random fluctuations of the phase of the complex hopping between the cavities, and no matter how large is the amount of disorder, these edge states stay there, signifying the topological nature of them. How much time do you have? 10 minutes. Okay. I think I'll need less than that.
Actually, if you don't leave time for questions, otherwise let's say 5.
All right. I think I can make it in 5. So the positive realization is again with this by plugging in the resonators with coupling elements within the artificial plasma, or the idea which Dr. Kyle in the previous presentation showed to you, with one D array of sinusoidal coupled waveguides. So if you make it finite, such a lattice, it's possible to find some zero-dimensional modes at the edges, at the two edges of a finite chain. And the last thing I want to show you is how one can simulate Dirac physics within metamaterials. So actually, metamaterial probe is this material. Actually, it's a three-dimensional lattice made of not atoms. These are not atoms. These are clusters of nanoparticles. Each single small sphere here is it's an 8 nanometer radius gold nanoparticle. The average radius of the whole cluster is 43 nanometers. So This is a plasmonic material which shows what is known in the metamaterials nomenclature is a negative zero positive refractive index. So this is what matters here. This is the generalist point, which does the whole Dirac physics in our case. This is the dispersion relation for waves propagating inside such a metamaterial. The thing is that originally such materials were proposed for achieving zero refractive index. So zero refractive index materials are very important in terms of technological applications because they are very nice collimators of electromagnetic waves. No matter at what angle light is incident on such a material, then when the refractive index is zero, then they get the same phase within the material and they get completely, absolutely collimated. But the thing is that because below and above the point of zero index, here we have negative refractive index because as the wave vector increases, the frequency decreases, and the opposite here is true. Here we have a positive index. One can actually simulate Dirac propagation in such a material. So this is the positive and the negative index region. This is the Dirac singularity. So again, we solve Maxwell's equations for such a system with the layer Maxwell scattering technique. This is dispersion relation. This is reflectance, absorbance, and transmittance of light incident normally on this material. As you can see here, the Dirac point, because this material is actually also lossy, because we are operating the optical regime and gold is a good absorber. However, the Dirac point is obvious by this dip in the transmittance spectrum. So one can actually measure this experimentally. And here we can actually see that the dispersion relation, this is for the imaginary part of the wave vector, agrees very nicely with the corresponding imaginary part of the wave vector provided by the Dirac equation. So this one is, the red line here is from the Dirac equation. The others are the ab initio electrodynamic calculations. There is a very good agreement. This offset that one observes here is due to the impedance mismatch between air and material, which is not accounted for by the Dirac equation. Otherwise, the two curves are almost the same. And with that, I would like to come to conclusions. I have shown you some photonic simulations for the integer, fractional, quantum Hall effect, topological insulators, Majorana edge states, Dirac physics. The systems which simulate this are various. There's a potpourri of them. They are in the microwave regime with coupled cavity arrays, for the integer quantum Hall effect, possibly with QED systems, dielectric waveguides, artificial plasmonic materials, optical metamaterials, and so on. So the trick here is to copycat the Hamiltonian problem to eigenvalue problem for the Green's tensor, which can actually be engineered with the coupled cavities and metamaterial elements. And it's the photonic systems are always a much nicer probe than electrons because interactions are weakly. Okay. So thank you for your attention.
It's time for a few questions. I have one. I mean, when you say Kane made a model and be translated to photons, because you don't need the breaking of time reversal symmetry. That's true, but that works because for electrons, for a Schrödinger particle, the time reversal operator is anti-unitary. That's the reason why K-Mel model works. Now, for photons, the time reversal operator is unitary because it's Maxwell equation. So that won't work in the same way. Can you comment on that?
Actually, I haven't seen that in this way. Actually, what I have tried is not to see it in terms of symmetry operations, but just to engineer the Green's tensor. Actually, I have the same matrix, the same thing as the Hamiltonian, and there are a few differences in that. But for example, I haven't got it in this. When you calculate the Caroline the modes for the Haldane lattice, then you get the opposite band structure than the electron. But all the general features are there for the Caroline states and that. So it's not exactly the copycat of the Hamiltonian. There are certain differences, and also in the edge modes, but the general features are there. I mean, the topological nature.
Other questions? I have another one since Mohamed is sleeping. Your Majorana thing.
I don't want to be a bad not sleeping.
I was hoping you would ask this question, so I'm asking myself. You see edge states. First of all, have you checked that this is not SSH physics rather than Majorana? You know there is this Su Schrieffer-Heger model that also
Yes,
has
yes.
edge states, and
Yes,
it's
yes.
less topological.
Yes. This is why I'm not calling it that it's the analog. I'm saying that it's the analogy with the same dispersion relation, but literally speaking, it's not Majorana. It's I'd rather call them topological zero-edge modes. And so yes, there is actually, and this publication was right at the same time when there was a photonic analog of the SSH model that you mentioned, and where in this case you need to have an interface between two different coupled cavity arrays. Then right at the edge, right at the interface of this change, we have this zero-dimensional mode. But I'd rather call it, as generally speaking, as topological zero-edge mode. So then that's completely.